So at the end of the last video, we took a look at the idea that the capacitance of a particular capacitor is not defined by how much charge it holds or how much voltage it has across it. It rather describes the amount of charge it can hold per volt across the capacitor based on something else. And so in this video, we're going to take a look at what is a capacitor and what defines the capacitance of a capacitor. Now here we have a picture from Wikipedia of several different capacitors. There's many different types, and they kind of look like batteries in some cases. However, they're not. Now you see most of these are cylindrical or maybe circular here in nature, but the capacitor we've been looking at is two parallel plates. So we're going to start there and just take a quick look at the fact that it can be cylindrical by having an outer plate that is curved into a cylinder and an inner plate that is curved into an inner cylinder. And the terminal of one of the capacitors might be coming from the core, and the other terminal would be coming from the external metal. So we could attach the battery over here across the capacitor this way. So just to kind of give you a visual that we actually are dealing with pretty much the same thing. The gap in between the two is going to be filled with the insulating material, and we will talk about that in a later video. So with that in mind, let's jump right in and see how can we actually change this value of capacitance. Well, the simulation gives away the idea that the plate area matters and the separation distance matters, as we can see over here. We're going to see that there are one or two other things that can actually affect this as well, and we'll get to those in time with the videos. So if I were to collect data on the capacitance of this particular capacitor as a function of the plate area, what I would do is collect data for the capacitance and the area, and if I were to graph those two quantities, so capacitance versus area, I'd find a direct proportion. Now we know that this graph is going to be y equals m times x, y being capacitance, x being area, and we have some slope value. So we could say that capacitance is directly proportional to area. If I collect data on the capacitance as a function of the separation distance, I see that the smaller the separation distance, the larger the capacitance. So the relationship between C and D is an inverse proportion. As the distance approaches infinity, the capacitance approaches zero. This would be an inverse proportion between C and separation distance. Now if I were to graph both the capacitance and the area over distance ratio, I actually find I get a linear shape, and this linear shape has a slope of the vacuum permittivity, which is very interesting and something that we have talked about several times. So the idea of the capacitance is defined by the vacuum permittivity, which is of the space between the plates, times the ratio A over D. Now that defines what the capacitance is, but then any amount of charge proportional to voltage across the plates can be gathered based on the capacitance of the capacitor. So obviously if we have more plate area, we can separate much more charge than if the area was a lot smaller compared to what it could be. So there's an interesting combination that you can do by looking at these two values. There are two different ways to calculate the capacitance. However, the Q over delta V form, this is more of the definition of the capacitance, and this here is what creates the capacitance in this regard. Now, if we look at the scenario over here, where we have the potential difference established across the plates, if I go ahead and turn off the electric field just to get rid of some lines, and I go ahead and change the separation distance, I see that because I have a battery fixed across these two spots, the potential difference is remaining the same. But as I change the geometry of the capacitor, hence I'm changing the capacitance, the amount of charge has to change in order for the voltage to stay the same. Or in other words, because the voltage will stay the same and the capacitance is changing, the charge has to change to stay equivalent to the potential difference. So in essence, what I'm doing here is that when the capacitor is still attached to the battery in this kind of cyclical process keeps the potential difference equivalent across the plates. And by changing the capacitance, I can store more or less charge on the plates. Now, we have an option here to disconnect the circuit and to put the capacitor, which is now charged, on its own. Now the charge doesn't jump the gap. The gap is an insulating source, so when the current is running through the circuit over here, it's only running through this side of the circuit and not jumping the gap. So when I separate it now, I'm preventing charge from moving. There's no difference in potential from one side of this little island to the other, so from here to perhaps here, so the charge can't move. And because the charge is fixed, now if I change the geometry of the capacitor, hence I'm changing the capacitance of the capacitor, let's do it with the distance, I see that the voltage has to change because the charge is fixed. So when capacitance changes, which is the ratio of charge or coulombs per volt, I see that when the capacitance is changing and the amount of charge is fixed, the voltage has to respond to the change in capacitance. So it's important to note when the capacitor is isolated, we have a certain scenario that occurs. What is occurring here is that Q is fixed, delta V must change to meet the capacitance. But when the capacitor is connected to a battery, delta V is fixed and Q must change, or can change, to meet the capacitance. This is a very interesting concept, and for some people it first seems a little bit counterintuitive, but if you think about the idea of conservation of charge and conservation of energy, it actually does make some sense. So go ahead and take a look at that, and in the next video we're going to take a look at the idea of charging and then discharging the capacitor and how this idea is actually possible.